Why? So simple means no proper ideals.
Proper ideals, yes. If there exists a proper ideal, then the proper ideal is an environmental subspace
Right.
of adjoint representation.
Right. And joint representation is just you take you send an element to taking a commutator with this element, right? But if you have an ideal, right, taking a commutator with some element brings you to the same ideal, right, by definition of ideal. So therefore it's in invariant subspace, right?
So we the main goal, main force we use to prove the joint. Main goal we need to use to prove this statement is the formula of some representation of GL. The dimension, the formula of the dimension of the representation of GL. Mm-hmm. So if
well, you need to say like, yeah, some highest weight.
The highest weight.
So this is called Wales dimension formula. Wales formula for the dimension of reducible representation of a highest weight lambda. And we obtained this formula in the last seminar. Remember, there only 3 people who was in this seminar. Hopefully, some more people watched the recording. So we had the Wales formula for characters, right? Which says that actually character is a sure function, sure polynomial.
And
right?
One thing we should I should remind you is these things it's not the highest weight of this guy. It's the highest weight of this guy.
Yes.
Means the representation of maybe on the singular vector. Maybe
So this is what's called as GLN weight, not SLN weight. So
because this element is not in
SLN.
But basically, these two, the representation theory of SLN and the GLN is the same thing. Yeah,
up to an action of the center.
Because this is just SL
Mm-hmm.
Yeah. So we consider this representation, the joint representation of SLN is the same too, and we can also act like consider it some kind of representation of GLN. So then we consider the joint representation as representation of a GL group algebra.
Yeah, by the way, is a joint representation of GLN irreducible?
GL.
No, it's not, because it has one vector which is the sum of all.
Because
Mhm.
it's
Yeah, because it has ideals. So N is an ideal there, and C is an ideal, right?
So how we prove this this goal is to find a singular vector, means find some singular vector and prove that this singular vector generates a irreducible sub-representation, and this sub-representation is the whole.
Yes.
Is the whole space.
SLN, yes.
Yeah, and then how to prove it is the whole space, and just calculate by the dimension by this formula,
Mhm.
and we work at the. And by the way, the dimension of this algebra is what? Plus or minus one.
Mhm.
So the goal is to calculate something. This is equal.
Right. So we need to find some highest
highest
weight vector,
Yeah, yeah.
and it will be of some highest weight. Well, a singular vector, in our terminology, singular vector, it will have some weight, right? And it will produce some sub-representation, which is highest weight representation of that highest weight. So you take this weight that plug in inside this formula, and you should get n squared minus 1. Then we will prove that it's reducible. So now the task is to find actually this singular vector.
First, just write down the formula we always use to calculate the commutator. It's it's what? JK.
I think it should be
KG.
KJ, yes.
Yes, and so now we try to find the singular vector.
Mhm.
X on some vector, so 0, so this is for all I 1, 2. So if we find something which satisfies this formula, then we find some singular vector.
Sorry, why do we use EII?
Because
I think it should be.
belongs to
Which
here.
doesn't lie in the
Yeah.
SL2.
Yes,
SL
but the representation theory of this, yeah, all the representation space of SLN is we can consider it as a representation space of this. So, and something irreducible here is the same to say it's irreducible.
Yes, but I mean, this one vector is like the one that is not in SL.
Yeah, it is in SL. Yeah, we should consider the V in SL.
Now we're considering representation theory of GLN. We're trying to find some, say that SLN is an irreducible representation of GLN. So we can act by add of something that lives in GLN, right? But act on something that lives in SLN only. So V should live in SLN.
Prove that
So what's written there, I don't think it's true though, because singular vector means you act by EIJs where I less than J. So this would mean that the weight of this vector is 0, what you wrote. So it should be EIJs with I less than J. So you act by all upper triangular matches.
Let's change the and the EI and
I plus 1.
In our context,
Yes.
yes. I'm sorry.
yes, yes.
Uh-huh.
In this context, are the roots and the weights the same thing?
No. Roots are weights of adjoint
So
representation.
we act with adjoint representation only.
But we consider this is for okay. So this is terminology for simple algebra. GLN is not simple, though.
We do some calculation here.
We didn't talk too much about roots, but roots if we're considering SLN, which is simple, then roots are exactly the weights of adjoint representation. Yes. And for every simple, these are actually definition of roots.
So we try to solve that one. So maybe we can try to see what happened for every basis of space, and so it is just follows that was definition E plus 1 G, which is and we want to get something 0.
Just to be pedantic.
So when it will be 0, we consider this to delta. So K must K must belongs to this set 1, 2, 3, 4 to n minus 1. So K plus 1 cannot be 1 because K start from 1, and the K plus 1 must greater or equal than 2. So we can take I here. I be 1. It will make this. It will kill this term. And about this, K cannot be n.
This was important correction, by the way.
Yeah.
Yes.
Yes. Because K cannot be n minus 1, so if we take G,
K cannot be n.
K cannot be n, so if we take G is n, then we kill this term. We get something. If
You want
so now we got a statement that E1n is a singular vector.
This one is the longest root, if you wish. E1n.
Yes, and we should consider what is the weight of this singular vector, and to calculate the weight, we should act PK. not 0, if and only if k is n. So it's 1. K is 1. And this term is not 0 if and only if k is n. So it is delta k1 minus delta kn. Yeah, and
So what is the weight?
the weight is so when we run out of all the k, we got something like weight is when k is 1, we got the eigenvalue 1,
Mm-hmm.
and k is 2, k is 3 is the 0, 0, because if
Mhm.
it's a 2, for example, if it's a 2, this 0, the whole thing is 0. And the last thing, when k is n, we got this term, minus 1. So this is the highest weight of this vector. And now we calculate the sub-representation that generated by this vector, and calculate the dimension of the sub-representation.
Mhm.
And we can see that it's equal to so how to compute it?
So lambda 1 is 1, then lambda n is -1, all other lambdas are zeros. So now plug this into this formula.
So we just use this formula. So we observe this formula. When these two things are equal, we got just some one term, because g minus I, g minus I. And if these two guys is 0, then this term is just 1. So we only need to consider when I and g take something, some different value, like 0, 1, or minus 1, 1, or minus 1, 0. Yes. And
So either I equals 1 or j equals n,
yeah, so we need to consider
or
only
both.
I equals to 1, and yes, and g whatever, and I is not I is a greater is greater than less than n, and g is and the last term I is she is greater than, and the last term is I is 1, is n.
Mhm.
So for this term, we got for this term we got this I is 1, so we fixed I. We just g from 2 to n minus 1, and I is 1, so here is 1 minus 0.
Mhm.
1 minus 0, 1. 1 g, and I is 1.
Mhm.
And g minus 1. So it's g.
Right.
And it is just 2 times 3
n minus 1 factorial right over n minus 2 factorial.
This term.
So n minus 1 factorial over n minus 2 factorial is n minus 1.
Yes, yes.
Oh.
And about this term, first we write I from 2 to n minus 1. And if I is this part I, then lambda I is 0, G is
Negative 1.
negative 1, so plus 1. Yes. Plus 1, 1 plus G, G is n, n and minus
Minus I.
minus I, yes. And here is n minus I.
So basically the same thing.
Same thing, yeah. What's this?
Just change the I to n minus I, and this will be exactly. Change n plus 1 minus I to j. And this will be exactly what's written on the top.
Yes. So it's yes. Minus 1 again. And this thing will be just one term. And it's 1 minus 1 is 2. And G is n. I is
1.
1. Yes. And so
N plus 1 on the top.
n plus 1 on top. And here should be n minus 1. Yes. And then we multiply them together. We got n minus 1 times n plus 1 and minus 1. So this is this.
Right.
This is and that is the definition. That is the
Dimension
dimension
of
of SL. And
Yes, very nice. Any questions?
First, we found the invariant space of the adjoint representation.
Yes, we did.
Then
Yes.
we calculated the dimension of that space.
Although not adjoint, but SLN. So adjoint of GLN is GLN. SLN is already invariant subspace of an adjoint for GLN. So now we would like to prove that SLN as a representation of GLN is irreducible. Okay. So how do we do this? We take we found a single vector, which is E1n. It is of weight this one, 1, 0, 0, 0, 0, negative 1. So if you take this vector and act by GLN on it produces some sub-representation inside SLN, right? And this is actually irreducible representation of highest weight this one. So inside SLN, there is an irreducible representation of this highest weight, right? So now we would like to see
But then this superrepresentation
is everything. That's what we would like to see. So you know dimension of SLN, it's n squared minus 1. But also from the general theory, you can compute the dimension of every reducible representation of GLN using this formula. So in particular, you can compute dimension of representation of this highest weight. You just take this lambda, plug this inside this formula, and get a number. And it happens that the dimension of reducible representation of GLN of this highest weight is exactly n squared minus 1. So it coincides with dimension of SLN. So inside SLN you have sub-representation, irreducible sub-representation of this highest weight of dimension which equals the dimension of SLN. Therefore SLN is just this irreducible representation.
Okay, so we know that we saw this in the first class.
Mm-hmm.
If we have E and G quotient by
Mm-hmm.
I,
Mm-hmm.
if they are solvable, then we prove that G is solvable.
Yes.
But we didn't say anything about nilpotency.
Mm-hmm.
Okay, and the thing is, in this case, it will not be true. We need something more.
Mm-hmm.
And in this problem, we need to prove what would be this statement here.
Mm-hmm.
So we need to, for nilpotency,
So if you replace solvable with nilpotent in this statement, this will not be true.
But it will be true if we put an additional
Condition on the left.
Yeah, an additional on the left, which is the following. We will have G. Okay, I will do the. So in this case, we will have I, G quotient I, solvable, important. And here the additional thing, it would be for every x and g, we have this at sub x. This is a matrix, we can think as a matrix. This, the restriction, the action on I, must be nilpotent. If we put this additional requirement, then we will have an if and only G nilpotent.
And also you have both
Yeah.
ways, right? So it's equivalent. Mm-hmm.
Yeah. Okay. Okay. So I will prove. First, I will prove this one.
Okay.
Okay. Okay. So we have many things at hand. We want to prove that G is nilpotent. And let's see. I have here. Okay. Okay. Let's see. Maybe.
So the first problem.
First problem is
Just give a
counter example.
Doesn't really matter. We can do it in.
I can
You know,
do it later. I
Yeah.
forgot, but
Yeah.
I can do it.
Yeah. Okay. Let's since we started with this one, let's do this one.
Then I will give the counter example.
Mm-hmm.
Okay. So we have we have that I is nilpotent. So by definition, we have the lower this thing.
Mm-hmm. The lower central,
The lower central
series. Yes.
Series. It will stop at some point, so we have something like I in brackets I. Is 0. So it's for some j. Let's say j. This is 0.
Mm-hmm.
So we also have for a similar, the same thing, but for this quotient. So let's say call it K, for this, also 0. So we have these two things, this and this. They are both nilpotent. So then, okay, we also prove, it can be seen, the following thing. If I have homomorphism, this is for any homomorphism, we prove this thing that phi,
Sorry, homomorphism between which algebras?
between any algebras, let's say phi, it's any homomorphism, so you have this, we can say this is like commutation relation with this morphism. We have that this apply to L, is contained in J phi of L. Right?
Right.
So here in this particular case we have the projection homomorphism from G to this quotient. Okay, so we apply this property. We apply this in this case, this particular case. So we have phi, okay, pi, this is phi, d, j, okay, wait a second. I can do this. This thing is contained in dk pi of j of d. But
Which
this
is G over I.
Quotient I. Okay, so this is 0. Right?
Agree.
So this is 0 in the quotient. So it means equivalently it means that the lower kg is contained in I. Yep. So now we can use the additional requirement. It will be used now. So for now we have this is in I, and we would like to see that that this thing it will be 0 at some point. This with G. Okay. So okay. So we have that this is true for any x in G. So if we do something like this, let's say d k plus 1 in G, by definition is this thing. Right? Okay. But this is contained in I.
Right.
And this, if we fix just an element, x, by the assumption, by this property here, this matrix will be nilpotent. So let's, okay, we let this here and just, okay, so in particular, if I take just some element, I will have this thing. The action of this path, so x is nilpotent, as a matrix is nilpotent, so we will obtain, let's say, for some n.
Right.
Okay, so if I apply this matrix n times, it will be x, the n times.
I agree.
Okay.
Yes.
Okay, so yeah, so now I think, I don't know, I was thinking like from this we can conclude, because this is true for all x.
Yes.
So we can but I'm not really sure now that this was correct.
Mhm.
And we can include something like this is 0.
Yes, because there is a corollary of the Engels theorem that the algebra is, or a finite dimension of the algebra is nilpotent if and only if in its adjoint representation every element is nilpotent, is adjoint nilpotent.
Engels theorem.
Yes. So you cannot deduce it directly from here because n depends on x,
Yeah.
right? But using Engels theorem, but in Engels theorem, though, you have to use add corresponding to the whole thing. This is what happens here, right? Yeah. Well, yes. Okay.
Yeah. Okay, so yeah, this is proved.
Okay. This direction is proved.
Yeah.
I agree.
Now the other from here to here. Okay, but I think this is the easy one because we need to find an ideal such that this is nilpotent, but we consider the commutator GG. So you take I as G. It's an ideal in G, and yeah, and we have G nilpotent, an ideal. This is nilpotent. Ideals of nilpotent.
Nilpotent.
So, and also G quotient I is this thing. Is abelian.
Right.
If it's abelian, it's nilpotent. So yeah.
Yeah, you can take I to be 0.
Yes.
But it's actually true if I on the left, I don't know how did I formulate the problem, but maybe it would be more interesting if I put like for any ideal such that this happens. Right. So for any nilpotent ideal such that G such that G of over I is I don't know. No, maybe it's okay. Yeah.
Maybe we should not to state that I is nilpotent.
Sorry again. Say it again.
You state that I is nilpotent and G mod I is nilpotent. And I say that may not need to say I is nilpotent. Just say I is an ideal.
Why?
Because the whole property.
So if you, so what's the statement? Can you spell it out?
I is an ideal and G mod I is nilpotent.
Right. And then this statement.
The same. And then this is equivalent to G is nilpotent.
So say we never used that I is nilpotent here, right?
And even I.
Right. We use only nilpotency of G of over I. This way.
Yes.
Yes. Okay.
Okay.
Yes, you're right. That's very good. Okay. So what about counterexample though? If we don't have this additional statement.
Okay. Okay. I used previous exercise from the first seminar. I think someone proved that this B, right, for a full flat, This is not nilpotent. Not nilpotent. Yeah, these are the
Right. This approved.
the
Yes.
upper
Okay.
triangular matrices, and we have this.
This
strictly-
was yes. This was nilpotent.
Yeah, strictly nilpotent. And if you compute the quotient diagonal matrices,
Right.
which are commutative, nilpotent, sorry. Yeah,
So this works.
so it works.
Okay. Thank you very much.
Okay.
For any Lie algebra, there exists a unique nilpotent idol. So we need to prove that for any Lie algebra there exists a maximal nilpotent idol with maximal dimensions. So if you have like two different ideals which belong to this, first we need to prove that the two nilpotent ideals, these are we need to prove that the sum of these two nilpotent ideals is also a nilpotent idol, because then it's just we can just know that it is the maximum. So suppose we have these two ideals and we have some element and some element that belong to these ideals. Then we can consider a sequence of sub representations in the adjoint representation, like
So adjoint representation of G. Okay. Yes.
yeah.
Yes. Okay. Very good. So what is this sequence?
This is just the sequence in the adjoint. Maybe I should write it differently. Actually, I read that for any finite dimensional representation of any Lie algebra G,
Right.
if you have any finite dimensional representation of this, then we can find a sequence
So
in this representation.
so you're doing like a composition series, right?
Yeah.
Okay.
So
That we discussed in lecture. Okay.
something like this.
And so the quotient of vi plus 1
Yeah.
by vi is
Yeah, or we
reducible.
can just say something like exactly. The quotient is simple, it is simple.
Simple and reducible is the same.
Yeah.
It's the same thing.
So we can take this for our sequence. In
Okay.
our sequence.
Okay.
And in this representation, we have like this. And also this. These are also nilpotent.
Sorry, I cannot read what's.
VA. One second.
So these are images.
Yeah.
If we
images
take
of the-
if we take quotients.
Yeah.
But what is YVI? Sorry, I just cannot read what's going on. So first of all, you have X and Y, right?
X and Y.
Are these related to this X and Y? And if they are, how they are related? I just don't understand your notation. So what this means?
This is a.
Maybe when we take the commutant of the sum, that would be in the, like we take the commutant a few times, that will be contained, as I know, in some powers of the sum of the power of I and plus about the power of j, like separately.
That's true, actually. Yes. But I think that's not what person going where he's going. So.
I'm sorry, but why can't we just use the linearity of the bracket and the fact that...
You're saying, I think, the same thing that Abner is saying. But since Prasun is giving his presentation, so let's let him go his way. So let's try to understand what are these guys. Right? So what do you really want from the composition series? So
I want that.
How do you want to use it? So maybe then we can figure out what are these things.
If I can find that this can be also nilpotent,
Right.
then this will imply that x plus y is also nilpotent.
This will imply that I plus j is nilpotent. I agree.
Yeah.
Yes.
I think I don't know what I'm thinking.
Yeah. Okay. So. Yeah, I thought, yeah, so I don't know why do you need composition series? I never thought in this way. Maybe this might be something, but okay. So, okay, if we are stuck here, yeah, maybe you will recall what was going on, but okay, so let's do...
No, I wonder if Prasun is looking for, like, construct another, like, this...
sequence
of like both for the sum of the two ideas, right?
Yes.
Maybe.
But Prasun was talking about this composition series for G.
Maybe it works if you take like homogeneous like sums.
I don't know. I don't see. Might be a good. I don't know. Never thought about using some composition series. Might be, yeah. But okay, so let's go with just a straightforward approach. Okay. Yeah, thank you.
Okay, from here, when we take Nilpotency. This like multiplication for different sides of elements in each idea. So these elements can like for example, the A's are in I and B's are in here. And they can look like just words different way, like this. And each of these ones will be in I or in J. It depends on which side you can choose. Like this could be.
So we are trying to take some element from here, like arbitrary element, and would like to see how it looks like.
Some tokens.
Okay, so we don't have multiplication though, right? This is for ring,
Okay.
for ring theory, right?
Yeah,
in our case, we have Lie brackets.
Yeah, the brackets look okay, like multiplication with the brackets can look like.
Yeah, so maybe.
This multiplication, but with brackets, like something.
Okay, but these A's and B's, they are different, right?
Yeah.
So maybe let us formulate it like this. So take an element, some element, I don't know, D from here. How does it look like? It's a linear combinations of elements, and we can assume it's actually not a linear combination, but like just an element like this. So you have D1, D2, D3, and so on, right? And then you have like dk minus 1, dk, and bunch of brackets here, right? So this is your arbitrary element in here, where each di is actually in I plus j, right? Therefore, di I can write down as xi plus yj, where this lives in I, right? And this lives in j. Since each di is like that, I can just decompose it like that, right? So therefore, this thing is a linear combinations of what you wrote down, right? So you have x, it's a linear combination of such things. Say x1, then x2, then y3, then x4, then say, so I can choose in each, so my indices, they grow, but at each point I can choose whether I take x or y, right? So maybe here I take y5 and so on.
Because they are ideal.
So these are your a and b's that you wrote there, but I have indices, right, now. So they are not the same elements. These are not just element x and y, taken in different orders. So these are different elements, but x's are from I, and j's from and y's are from j.
Yeah, like there's a minimum. There are minimum number where.
Yes.
For example, the k of j is equal to 0, and the n of I is equal to 0. And in this case, each time
Yes.
we take the bracket, it would be in I or in j because they are ideals. So at the end we will have a finite multiplication of only in one ring,
Right.
or in the other, and if it's more than one of these, it's 0. So if yeah, it's like that. Like because they are ideals, they enter again in the ideal, something like that.
Right. So actually, so with this k, right? What you're saying with this k, your this element lives in d. I don't know. So k1 is the number of elements x in here, right?
These sums we can
Of I intersect d k minus k1 elements. So if I take k1 x's, then I have k minus k1 y's, right, in here. So, and the y's live in J, right? So why is that? I cannot actually, like, switch y's and x. So these operations are not do not commute, right? But all this d with lower indices, they are actually ideals, right? So when I take, suppose this, I'm checking this part. When I take commutator with x, I kind of increasing this index, right? But then when y appears, right, I do not lower this index because it's an ideal, right, or whatever. It's still, since it's an ideal, I just keep commutator with y, I will still be in the same d with the same lower index. And then again, meeting x, I will increase this index, right? It's the same, and the same, so since I met like k1 x's, right? This will be in dk1 I. And when I now counting how much y's I met on the way from here to there, this will be, the same argument tells me that it's in dk minus k1 of j. But then if my k is big enough, right, either k1 is greater than k. This k is not the, so maybe I need to choose it to k tilde, okay? So this is different k from this one, right? So if k tilde is big enough, it's either k1 is greater than this one, and this is 0 then, or k tilde minus k1 is greater than n, right? So I actually have to take k tilde at least k plus n, right? Then this, all things like that will be zeros. And so we will have that dk plus n. What we proved, yes, so what we have is dk plus n of I plus j is 0. And so I plus j is nilpotent. But we proved that I plus j is nilpotent. So how to proceed out of that? Right. So how to finish the problem then?
That was solved, I think. That it's.
No, we need to prove this, right?
Yeah, if this is nilpotent, so at the beginning we take I and j, maximal of dimensional. So
you take, yes, okay.
So this should be here, and so one of two. This should be the same at the end. So j should be the same. Yeah, because okay.
So you take I to be nilpotent of maximal dimension. That you can do because G is finite dimensional. Okay.
And we take another one, J, also
yes.
of maximal dimensional.
Yes.
And then A plus
No, J is not maximal. So J is some other nilpotent.
Okay, just nilpotent.
And you would like to prove that it's inside I then?
This is the maximum.
Yes.
So this is again nilpotent, and dimension. It's greater or equal to the dimension of I. Oh, this is not possible because in this case also I is contained here, and then this will be.
So
it's
it's
not possible because I is maximum.
right.
So it has to be
Equal.
the same dimension.
So therefore I is
Containing I.
yes. So J contains in I is contained in I plus J, but I plus J equals to I. So J contained in I. So every nilpotent ideal is contained in an ideal of maximal dimension, of nilpotent ideal of maximum possible dimension. And so we proved.
I think whether we can still use the previous problem to.
Okay. So if you would like to show us how, we would be happy to hear. Thank you very much, Adnan. So new radical is the ideal that we found in the previous problem.
And actually we can do this. We can quotient nilpotent radical. All the same.
Okay.
So if we quotient
So nil intersect radical.
So we prove this is
Right, so nil is not inside, right? Should be intersect.
not. It should in this because nilpotent is also
Nilpotent are solvable, but you have nilpotent, but you have solvable which are not nilpotent, right? So therefore radical is bigger than. No, I think. So sorry, I think you're right. Yes.
It's not important.
Yes, it's not important because you're right. Otherwise, it would be important. Yes. Okay.
So this statement is equivalent to this thing. So we just need to prove something like we just need to prove that if has no nilpotent ideal, then so we change our goal to prove this statement because of
So you're saying that, okay, this implies this, but from here to here, how you go?
from here to here, we just say that if here to here. And we consider the map projective to
New? Mm-hmm.
and just use. So this is homomorphism of the algebra. This to it. 0, the inverse of 0
No,
will get the nilpotent. And
so actually you should argue. Yeah, okay. So pi of g radical g is this, because pi is homomorphism, right? So therefore it's 0. Therefore g radical g should lie inside the ideal U quotient by. So nil g. Right? So what leaves? So therefore this is in the kernel of pi. What's the kernel of pi? Nil g. So therefore this guy is inside nil g.
yeah, and
Yes.
this is
And therefore this implies this back. Okay.
So they are the same thing.
Yes. Okay. So now you would like to prove this one.
Yes, actually this one.
So-
If G has no nilpotent ideal, then this is 0. So if it has no nilpotent, then what? Yes.
So you're saying that. So what's the relation between this statement and this statement?
Because
So without P.
this is the algebra without nilpotent.
Yes.
Yeah. So
But you need to see that this is the radical of this algebra also.
right. So we go back to here, and
Uh-huh.
this is a radical. No. We should consider any radical here, and consider
Any yeah, I is solvable ideal in G.
yes, and there is one correspondence between each other. How to say it?
No, I think you should take I, which is solvable in here,
Yeah. So okay.
consider its preimage,
Right.
which will be solvable here. Right?
Yes.
So it, and then it's solvable here, therefore it lives in radical.
If we take some.
Therefore, when you take the image again, it will live in radical quotient by new radical.
And we go back. This is
Okay, so does everybody understand what's going on? So again, we would like to show this. Okay, then the first statement, so maybe without pi. These two statements are equivalent. From here to here, it's clear. From here to here, you just need to use that projection is a homomorphism of real algebras. Now let us try to prove this one. Now the second statement, that this implies this, right? So this is Lie algebra with no nilpotent ideals, because we killed one. Every nilpotent ideal lives inside nil G. But what we're trying to see, that this quotient is the radical of this quotient, right? Then if we prove this statement, right, then this will be the radical of this. This will be 0, and this will imply what we would like to prove. So now the goal is to see that if my G prime is G quotient by nil radical of G, then radical of G prime is radical of G quotient by nil G. So that's what we would like to figure out.
I think actually we just need some weaker statement if this is a solvable ideal.
Yes.
So like this is a solvable ideal, and then all the solvable ideal here. Go back to it's solvable means
No, pi inverse of J is solvable because J is solvable, right? Which is quotient of this by solvable ideal, which is nil G. So J is quotient of this by nil G. So quotient is solvable, nil G is solvable, therefore this one is also solvable.
right. So then we know this.
Right? So therefore this guy is inside radical. Right? So therefore G is inside radical by G by nil radical. So every solvable ideal in here lives in here. So therefore this thing is the radical of G prime. Okay, so what's left is to prove this statement. If G has no nilpotent ideals, then it's reductive.
We know that solvable algebra, the commutant of solvable algebra is always nilpotent. So, but the nilpotent is we don't have nil. So this we have this radical is 0.
Yes, I agree. So radical is solvable. Commutant of solvable algebra is nilpotent, but G has no nilpotent ideals.
So we have this. So
I agree.
and then we consider this.
I think I made a mistake, but I
Mm-hmm. Yes.
and this is not potent because this is solvable. So this is so when we repeat this inside.
So this is nilpotent, I agree. But this is not inside. I'm sorry.
The commutant is this inside here.
So how this is inside?
Because this is in graph and the other thing also is in graph.
So this is in radical.
And the other thing, because this is over here, it's also in radical. And the one where no is like this.
So because of we don't have nilpotent and I know.
So let us not be talking after, because I don't see why this is.
Because this formula tells us that radical is nilpotent, and we don't have nilpotent, so radical is 0. Is 0?
Radical is nilpotent, that's true. So you're saying that radical is abelian, right? But abelian is nilpotent.
Radical itself is nilpotent
That's not.
because of this. Right.
Radical is
No. Radical is solvable.
No, I'm not. I said, from this formula, we know the radical times radical is 0, so radical is nilpotent.
So you're saying that yeah. So you're saying that radical
Is
is
a
abelian.
So,
No, yeah. So
Yeah,
radical
it's
is abelian and hence nilpotent.
yeah, it's nilpotent, and we don't have nilpotent, so radical is 0.
Seems like
Sorry, can you repeat your last word?
yes. Did you trick us? Let's see. Again, let me try to repeat. So maybe. So we're proving this. So G has no nilpotent. So if nil radical is 0, then we have this. Let's try to prove this. Radical is solvable. Therefore, commutant of radical is nilpotent. So therefore, this thing is nilpotent. But it lies inside nil radical. Therefore, but nil radical is 0. So therefore, this should be 0. Right? But this is the first element of whatever series you choose, a derived series or lower central series of radical. And it's already 0. So it means that radical is nilpotent. And it means that, but since G has no nilpotent ideals, radical should be 0. So G is
G also has no radical.
G is semi-simple. I think it's not. Might be true, actually.
It's true.
So, for example, GLN, right? Let's see. The radical is scalar matrices, right? But it's also scalar matrices are abelian, so the radical is nilpotent, so it has nilpotent, right? I don't see mistakes. I don't know. No, I cannot think of any counterexample. So, yeah. So maybe this works.
And if problem 4 is true, then problem 5 is just use this.
Yeah, problem 5 is just use this. So let me actually prove this statement using our results from the previous lecture. What I would like to say, so I would like to see that this thing is nilpotent ideal, right? So basically, this is what it says. This is nilpotent ideal. It means I would like to use the following, that G radical G acts by 0 in every reducible representation. That's what we proved last time.
What do you mean by the column?
Yes, sorry. Every reducible representation of G. So let me take G itself as a representation. It might be reducible, right? Just to apply this statement, I would like to consider composition series. So I have V1, V2, and so on. Vm coincides with V, and so Vi quotient by Vi minus 1 is irreducible. Right? So these are irreducible, therefore G, radical G, acts on each, so if this is Wi, acts on each Wi as 0. Right? It means that if I take an element from here, x, and consider rho v of x act on Vi, then the result will be in Vi minus 1. So this is equivalent to this, right? So it means that when I quotient by Vi, this should be 0. So the result should be in Vi. But this means that actually x acts on V by nilpotent operators. Right? So we have blocks. Well, if you wish, we have some partial flag, right? And this means that rho of V of G radical G is inside n of f, just by definition of n of f. Right, where f is this flag. So therefore, add x is nilpotent for every, so for every x from here, add x is nilpotent. In simple words, each time applying add x and rho v of x is the same thing, because v is an adjoint representation, right? So I apply one time, I go to Vi minus 1. Then second time to Vi minus 2. And so on, and then at some point I will get to 0. So add x is actually nilpotent for every x in here. Then by Engel's theorem, like the second Engel's theorem, this is nilpotent, and therefore this lives in nil radical. So this is something that's related to the lecture and also uses representation theory. But this one, I don't know. You spotted some mistake?
We want to prove this, right?
Right.
And we already have this. Right?
No.
No.
This is for
This is for G who has no nilpotent ideals.
So if you mod nil in both steps, then you.
Not every solvable
So
the algebras
I
are obedient.
have this, right?
Okay.
Okay. And then we consider second thing. We just consider the commutator of this commutator. I mean, this bracket is just the same for this. Then this and this is in right.
Sure.
So and you have this, and then you have this.
Okay.
Just repeat.
So this is nilpotent.
Yes.
So there are no nilpotent. This is it.
Yes. But it's just my proof with
Yeah, they're kind of the same.
with this quotient.
Yes, yes. Without the third statement.
And everything is same with my proof.
Okay, this works. Hopefully.